Section 4.2 covers computing p-values, which is what you have to do to determine if you have a statistically significant result or not. In terms of the workload for a hypothesis test, this is the majority of the work. As far as Groundhog Day is concerned, Punxsutawney Phil's predictions aren't so good. 47 correct predictions and 120 winners. So a natural question would be, is this worse than flipping a coin? We want to see if there's enough evidence to conclude that the likelihood of Punxsutawney Phil predicting the duration of winter correctly is less than 50%. There are a couple of big assumptions that we're making here. One is that 120 consecutive winners would be a representative sample. The other is that there is one Punxsutawney Phil, which is obviously wrong. After all, it's a groundhog, not a tortoise. Groundhogs don't live to be 120 years old. Just go with it for now. Generally, the statement that you're looking for evidence of is the alternative hypothesis. Like I said in section 4.1, I think it's easier to formulate the alternative first and effectively backsolve for the null. If we're going to do that, the key phrase is less than. So the less than 50% at the end, the less than in that phrasing dictates that there needs to be a less than in the alternative hypothesis, which is how I'm getting p less than 0.5. Then, for the null hypothesis, essentially all you have to do is replace the inequality with an equal sign, and that's all that I'm doing to get those hypotheses that are toward the bottom of the screen. Once the hypotheses are set up, the next step is to figure out how unusual our sample statistic is under the assumption that the null hypothesis is true. So whatever the null hypothesis is, all of the computational steps are done assuming that that is a true statement. To make this a little more concrete, we can do it with the Punxsutawney Phil example. We're going to assume that p is equal to 0.5. We're assuming that Punxsutawney Phil's accuracy is really equal to that of flipping a coin, because that's what the null hypothesis was, p equals 0.5. Under that assumption, what's the probability that out of 120 winners, he predicts 47 or less correctly? Since the 47 out of 120 was our sample proportion. We want to figure out the chance that he's accurate that often or less. That we're getting 47 out of 120 as a sample proportion, or something even more extreme, where more extreme essentially means farther away from 0.5. What we can do is we can simulate many samples with the same sample size of 120 and with that assumption of the null hypothesis that p equals 0.5. Once we simulate all those samples, then we can see how often we get sample proportions of 47 out of 120 or less. In the previous slide, we had the idea of simulating a whole bunch of samples that are the same size as the original under the assumption that the null hypothesis is true. When you do that and you compute a statistic for each one, you end up with a randomization distribution, which is, like it says there, a distribution of statistics from samples simulated under the assumption that the null hypothesis is true. From there, you can get an idea of how often you would get a statistic like the one that we got in our single sample, or something more extreme. There's a randomization distribution. If you look at those two buttons up at the top, that first one indicates single proportion. The second one indicates a 0.5 in the null hypothesis, and I have 5,000 samples simulated there. This is how you would generate a randomization distribution. For all of the stuff in Chapter 4, you want to be over here in StatKey, underneath where it says randomization hypothesis tests. The Punxsutawney Phil example is for a single proportion, so I want that. This is already set up here with the null hypothesis of p equal to 0.5, but there's a preloaded sample that we need to get rid of. So if I go to edit data and put our sample in there, we had 47 out of 120 correctly predicted winner durations. So then that way we're getting the right sample size. And then just like with what you would do when constructing a bootstrap distribution, you want to have at least 5,000 samples generated. So I'm just going to click on generate 1,000 samples 5 times. There's a randomization distribution. Once you have the randomization distribution, it's pretty quick to figure out how unusual the observed sample statistic would be under the assumption that the null is true. What you do is you use the observed sample statistic as a bound, and then the correct tail or the correct direction that you want is determined by the inequality in the alternative hypothesis. So in this case for Punxsutawney Phil, there was a less than in the alternative hypothesis, which means that we're going to want a left tail. This is what you would do. Notice in the upper left of the screenshot, I have left tail selected. Basically all I did was select that, and then I specified the bound on the tail as 0.392, which is what you get when you round to 3 places, dividing 47 by 120. Now I can show you how to do it since I have it here in StatKey. You just have to go up here and select left tail in the upper left, and then I'm going to click on this number down here that's the bound for the left tail, and I'm going to change it to 0.392 because that's what our sample proportion is if you round to 3 places. You can see it in the original sample box up here, the 0.392. That's where I'm getting it. And this right here, that's how often you would get a sample proportion of 0.392 or less if P was really 0.5 and we repeatedly took samples of size 120. So like it says at the bottom, 0.011, at least in that picture, would be the p-value. The proportion of randomization statistics that are in the tail bounded by our original sample proportion. Here's the general definition of a p-value, which is kind of wordy, but there really isn't a way for me to shrink this down at all. So what a p-value is in general is that it's the chance of obtaining a sample statistic at least as extreme as the observed sample statistic, assuming that whatever is in the null hypothesis is a true statement. The way that you compute it, which is basically what we would do to get that 0.011 that's on the previous slide, it's the proportion of statistics in the randomization distribution that are at least as extreme as the observed sample statistic. So for the Punxsutawney Phil example, without the context, if p equals 0.5, so there's the assumption that the null hypothesis is true, there's a 1.1% chance of getting a sample proportion, a p hat, less than or equal to 0.392 with that sample size, with n equal to 120. Or, to make it a little bit shorter and a little more symbolic, if p equals 0.5, the chance that p hat is less than or equal to 0.392 with the sample size of 120 is 0.011. Now with context, with everything in there, if there's a 50% chance that Punxsutawney Phil predicts the duration of a given winter correctly, so that's if the null hypothesis is true, if p equals 0.5, the chance of him predicting the duration of 47 or less winters correctly out of 120 is 0.011. Writing out the p-value is kind of long-winded. There's no way around that. We know how to compute a p-value, but what does it mean? What does that tell you? What does that 0.011 tell us in the Punxsutawney Phil example? Well, the way that it works is if you have a small p-value, that means that the statistic you're getting would be unlikely if the null hypothesis were true. And that's where you say, well, in that case, then maybe the null hypothesis is wrong. Maybe that assumption that we're working under is incorrect if the thing that we're getting out of our sample looks really unusual under the assumption that it's true. Generally, the smaller your p-value is, the more evidence you have against the null hypothesis, which would be the same thing as saying the more evidence you have in favor of the alternative hypothesis. So little p-value means that it looks more likely that the alternative is actually true and the null isn't. This is nothing new, that you can have 3 types of inequalities in the alternative hypothesis. But what you do for a 2-sided alternative is a little bit different than what you do for a 1-sided alternative. Because for a 1-sided alternative, you just have a single direction that you have to worry about. If you have a less than, then it's a left tail in the randomization distribution. If you have a greater than, then it's a right tail. But if you have a 2-sided alternative, the not equal to, there you have to consider both directions, so it's a little bit different. What you have to do for a 2-sided alternative, your sample statistic, whatever it is, in the randomization distribution, either what's in the randomization to the left is smaller than what's to the right, or vice versa. Basically, you just take the smaller tail and double it. So we're about to go through an example of that because this doesn't make a whole lot of sense without an example. This example has a 2-sided alternative. We have the sample of 20 current FICO scores, and it says that last August the average FICO credit score was 695, and we're looking for evidence that it's changed. Right before the question mark, no longer 695. There's no specified direction there. It's not asking, Do we have evidence that the average FICO credit score is now less than 695 or greater than 695, just that it's something else? So this is where you need the not equal to in the alternative hypothesis. This will be a two-sided alternative. Setting up the hypotheses, that's what you end up with. We know we need a not equal to in the alternative. This is for a single mean, so the parameter should be a mu, and we're looking for evidence that mu is something other than 695. So the alternative should be mu is not equal to 695. Back solving for the null, you get mu equals 695. What the p-value will be here is the proportion of values in a randomization distribution at least as extreme as the sample mean, which is 712.5. That's what you get if you add up all of the values in the sample and divide by 20. So we know what our cutoff is supposed to be. If we had a greater than in the alternative hypothesis, this is what we would do. You would select right tail in the upper left in stat key, and then you would specify the right tail cutoff as 712.5, and the p-value would be 0.185. However, we don't have a greater than, we have a not equal to, so we end up with this. The only difference is that I picked two tail in the upper left instead of right tail. The only thing that I specified was the 712.5. The left tail stat key will duplicate one that's the same size. So basically stat key, once I put in the 712.5, it computes the right tail, gets the proportion of 0.185, then it generates a left tail that also has a proportion of 0.185. And it gives you the cutoff that you don't really need here of 677.25. Notice that the cutoff is not the same distance away from 695 as 712.5 is. That's okay. That's really just due to randomization in terms of the way the distribution is constructed. That's fine. Really, it's just doubling a tail of the same size. The p-value here would be 0.37, which I guess you could get either from adding the two 0.185s together, the left tail plus the right tail, or just doubling the right tail. Either way, you end up in the same place. If you're going to do this in StatKey, you need a test for a single mean, since there's no comparison here, but it's certainly quantitative data. Then I need to get our data in here. So if you go to Edit Data, delete the preloaded data set if StatKey will let me. And I have it here. And I need to change the mean because I don't want 98.6. I want 695 in the null. And then we can generate 5,000 randomization samples, and then two tail. And then the idea of the smaller tail being doubled, that's why I'm putting the 712.5 here, because 712.5 is bigger than 695. So if I put the 712.5 here, then it's this tail, the smaller tail, that's getting doubled. If you look at the picture, left of 712.5 would be the majority of the distribution. That's the bigger tail. Right of 712.5 is the smaller tail. So going back to the definition about how you would handle this, that's what it means by smaller tail. I get something slightly different here than what's in the slides. I'm getting 0.364 instead of 0.37, but that's okay. That's just random variation. Another example, this one is for a difference of means. We have prices of compact cars from Enterprise starting at 10 randomly selected dates during the next 6 months. Well, next 6 months from when I did this in the spring. And what we're going to try to figure out is if on average it's cheaper to rent a compact car at the larger airport, which is certainly Sky Harbor. The Mesa Airport is not very big. I think in terms of enplanements, Sky Harbor is number 2 in the US. It's number 2 or number 3. Because of the word cheaper, the alternative hypothesis should be one-sided. And specifically, we're looking for Sky Harbor being cheaper than Mesa on average. That's the kind of orientation that you want in the alternative hypothesis, the way I have it written out there, where I'm using P for Phoenix and M for Mesa as subscripts. I suppose you could write this in the opposite order, as in mu sub M greater than mu sub P, but I wrote it the way that I did to match up with the way that it's phrased in the wording. We have a one-sided alternative this time. There's our original sample box with the data entered. Because there's a less than the alternative hypothesis, there's no need to double the tail, so 1 multiplied by the proportion in the tail. You don't really do any multiplying. It'll be a left tail because of the less than the alternative hypothesis, and bounded by the difference of sample means, which is negative 53.2. You can pull that directly out of stat key right underneath where it says original sample. I intentionally put the 2-tail randomization dot plot in the notes just to point out that if you did select 2-tail by accident, you could still get the right answer. You just have to ignore the right tail. The only thing that we want is the left tail bounded by negative 53.2, so the correct p-value here would be 0.014. Generating this in stat key, this should be a test for the difference of means. Then we need to get our data in here. So I'll have to dump the preloaded data as usual. And I've got it in this text file where I used P's and M's for Phoenix and Mesa. Then generate 5,000 randomization samples. And this one I'll do it the right way and just say it's a left tail. And we want that to be bounded by negative 53.2. And this time I happen to get the exact same p-value that I have in the slides. One more example, the difference of proportions, since we haven't covered that yet. The row that's in yellow is there because I think it's weird. That would represent people who don't know if they own art, which seems kind of impossible. It seems like that's something where either you have it or you don't, that there isn't much of a gray area. I suppose unless it's something like this. Maybe somebody thinks, well, I have this painting, and I don't know if this is really art. Maybe that's the thought process that's going on with the people who say they don't know if they have art. Anyway, the 2 proportions that we're going to compare, we have that 123 out of 409 adults with a family income less than $40,000 a year said that they own art, but 110 out of 180 adults with a family income greater than $80,000 a year said that they own art. Is this enough evidence to conclude that the respective population proportions are different? So because of the word different, we need a not equal to in the alternative hypothesis. I figured the best I could do for the subscripts to try to keep it kind of descriptive was to use 40 and 80 for $40,000 and $80,000. If that looks weird, I guess you could use other stuff, but that was the best that I could come up with. There are sample proportions. So for the less than $40,000 group, p hat sub 40 is 0.301. Then for the more than $80,000 group, p hat sub 80 ends up being 0.611. So the difference in sample proportions is fairly sizable. I should also point out that if you used the reverse order here, so p hat sub 80 minus p hat sub 40, and you'd get positive 0.31, that's okay. There's nothing wrong with that. The order is essentially a preference, and I'm just matching the order they show up in the wording. Here, we have a 2-sided alternative, so we do have to multiply by 2. And based on the way that I have things set up on the previous slide, we're going to be doubling a left tail bounded by negative 0.31. If you use the reverse order of subtraction, you would be doubling a right tail bounded by positive 0.31. That's fine. You'll get a comparable answer. Effectively, you'll end up in the same place. And here, this is what you get for a p-value. In a way, you can see this coming because the difference in sample proportions is huge. It's above 30%. You get a p-value of 0. The picture looks a little bit weird because the randomization distribution isn't centered. The reason that that happens is the only thing that I specified was the negative 0.31, and that's way out there to the left. So there's nothing beyond it. That's why there's a 0 in the left tail. What's going on with the right tail is that when stat key duplicates a tail of 0 on the opposite side, it only goes out as far as it has to. And it doesn't have to go all the way out to positive 0.31 to get a 0 in the right tail. It just has to get past the last dot in the dot plot, which looks like it's at about 0.182. That's why it's off-center. It's because stat key only goes as far as it has to get the 0 on the right side. If that happens in the homework, or if that happens on the exam, Or if that happens when you're doing the project, which is eventually going to happen, that's not too far into the future now, that's okay if your randomization distribution isn't centered. It's just that's the way that StatKey generates that other tail. And we can also generate this one in StatKey. This should be the difference of proportions. So I need to get the sample proportions in there. 123 out of 409 for less than 40,000 and 110 out of 180 for greater than 80,000. And generating 5,000 randomization samples. 2 tail, and then I just have to specify the left tail cutoff as negative 0.31. There. What I'm getting, generating this in StatKey, is pretty similar to what's there in the slides. My left tail, the bound for it, is so far out to the left that you get that lopsided looking picture, which is perfectly fine.